nothing goes wrong until you actually embed all of the neighbors of B. Anyway, they come first. So
Okay.
we will embed them
So we
first.
finish them.
So we finish them. And now at this step, when we finish them, which is exactly the step with number NH of B, right? Because we have already embedded all of the neighbors of B, we will stop and we look at these special vertices in G.
In G.
Right. So in G, each vertex may be the potential option in the future for some subset of the vertices in B.
Right.
If they are belonging to too few of these potential sets, then we separate them out into this set EI. We only want to keep the guys that will be useful for many Bs in the future. So we throw out those that are not very useful. And then we have already reserved this set DI in advance. So we will just embed DI into these destinations in EI.
We will make sure DI is larger than this EI, right?
Right. So EI will have to be small. We guarantee that by regularity.
So we're get rid of those bad vertices EI.
Yeah.
Now capital T is the currently embedded vertices.
Yeah. So maybe T will be pulled down here. So forget about T for a second. So let's just think about what we continue after the special step.
So what is the continue part? We continue.
So after the special step, we will continue just like what we do here. So next vertex, check the feasible set, check what will be an option for us, and put one option uniformly at random.
But you do
But
vertices that are not in B, right?
So now these are vertices that are not in B or the neighborhood of B, potentially. These are just vertices, remaining vertices, right? And once we hit the remaining vertices, the only tricky thing that we need to do is every delta 2 times n many steps. So whenever the index is a multiple of this parameter, we will stop. We will look at all of the vertices that have potentially too small a feasible set.
So XJ, what's XJ?
So Xj are the set of vertices
neighbors
from in the first J vertices in the embedding. Yeah, so they are just the first J vertices in the embedding. We're not constraining anything about the neighbor here. So these are just the vertices that have been used by the embedding of the first J steps, right? We cannot reuse them, so we throw them away. And these are the feasible vertices that we can use to embed the vertex B into. So in total, this is the feasible set. At this stage, because we have continued for a very long time, this feasible set, even under the quasi-random condition, this can be small. This can be.
So LJ is the vertices in H that are sort of hard to embed now.
Right.
So the feasible set gets smaller.
That's right. So yeah, so Xj are the vertices in H that have been embedded. Now for the rest of the vertices that haven't been embedded, so they are in H, we are looking at those for which they have too few options.
I see. So at every little checkpoint, you check which one are dangerous, then you move them
Pull them to the beginning.
Priority and then do them.
Right.
And then repeat.
Right. So yeah, that's one thing that we need to do in order to guarantee that things will run. So after we run this all the way to the end, so all the way until, so we will run this until we have only vertices in B that haven't been embedded. But some of the vertices in B may have been pulled forward, so they have been embedded. So we only have subsets of B that are not embedded at this point. So I'll let T be.
Phase 2 only starts when vertices outside of B
have all embedded. Right. So phase 2 only starts to embed the remaining vertices in B.
Okay.
So T, I denote the vertices that have been embedded before phase 2. And now we have the vertices that are not embedded yet in B. We have the options that are not used yet in the previous step. We construct this bipartite graph, which tells us what can go from B to like which pairs are feasible for the embedding. And then the perfect matching here would exactly mean one way to finish the embedding.
I see.
So, right. Let me note also that there are other proofs of the flow lemma, but still one common thing is all of them at some point would use some result that guarantees a perfect matching. So you can still then try use the same tool for finding a spread perfect matching in order to get via other means spread flow lemma. So somehow this spread perfect matching is fairly universal.
Any question? If there's no question, we're gonna resume tomorrow. Tomorrow, yes. Okay. Let's continue tomorrow.
Recording stopped.